Hi everyone, thank you for coming. We're going to be talking about dynamic object gaze tracking with OpenCV today. So before we get into it, just a little background about our lab. We're led by John Pearson over there, who you may have attended his Julia tutorial on Wednesday. And our focus is on computational techniques applied to complex behavioral and brain data, including a lot of machine learning. And if you're more interested in that sort of stuff, or you like what you see today in our talk, you can go ahead and check out our website at pearsonlab.github.io. We have some blog posts that go into more detail about what we did here, and links to our GitHub and that sort of stuff. So before I talk about specifically what we were doing, I thought I'd give a brief background on eye tracking. So eye tracking started in about the 1950s with a Russian psychologist named Alfred Yarbus. He performed these experiments with this complicated device that reflected light off the retinas, and then using film basically recorded where people were looking with respect to a piece of artwork. And you can see the experiments that he was running right here on the right side of the screen. Basically, he'd show one piece of art and then tell people to do different things with that art. So remember the clothes worn by two people, or give the ages of the people. And he found that the gaze patterns for these were drastically different depending on the task that people were given. So that was kind of the beginning of eye tracking. And since then, in modern times, eye tracking is used widely for everything from human-computer interaction to market research to psychology and neuroscience, like we're using it today. So basically, there are two modalities of this research. One is static eye tracking, which is what Yarbus was doing, where you're looking at an image and you're tracking basically where people are looking on that image. And nowadays it's done with screen-based eye trackers. So you're getting coordinates of where people are looking with respect to a screen with an eye tracker attached to it. And the advantage of that is that the analysis becomes a lot easier because you know exactly where everything is on the screen. But it's limited in that you're in a controlled environment where you can basically only track what people are looking at on a screen. So the other modality of eye tracking research these days is head-mounted eye tracking, including eye tracking glasses, which is what we were working with. The disadvantage to that is that analysis becomes a lot harder because you're only getting gaze coordinates with respect to a video camera on the eye tracking glasses. So our problem that we're trying to solve here today is how do we do complex analysis on eye tracking glasses data? So this is an example of what we were working on. Basically on the left we have a frame from our eye tracking glasses, and it's probably not very noticeable, but there's a blue circle near the head of the man in the piece of artwork, and that's just showing where the person is looking. And we're trying to translate that to this static image so that we have people that are if they're in an art museum, they're walking up close to the image, they're zooming out, they're doing all sorts of different things coming from different perspectives. We want to map those gaze coordinates just to this static image. So that's the problem that we're trying to solve. And before I show you what we did, I just want to show you the results so that you know what we're working towards in this talk. So you can see even when part of the image is cut off or perspective is changing, the mapping to the static image remains consistent. All right, so that's what we're going to be trying to accomplish. First, I want to talk about the hardware that we were using. So we were using the Tobii Pro Glasses 2. There's a lot of eye tracking glasses, but we found that these would be the best for our purposes for a few different reasons. One is that they have 4 infrared sensors that they use corneal reflection to create a 3D model of the eye. And by building that 3D model, that allows them to compensate for like glasses slipping down or like slight perturbations. So you get a more accurate gaze position readout. Another nice thing about them is that they have an accelerometer and a gyroscope, so that they track motion during the experiments that we run. And the best thing about them is that they implement a REST API. So you connect to them via Wi-Fi, and then all of your interaction with them is via HTTP calls. So it's language agnostic, and you're not forced to use their proprietary software for data collection and analysis. So we were able to create our custom solution. And a little bit about the software that we used. We used OpenCV for our image analysis, so we did it frame by frame. FFmpeg for encoding and decoding video once we had the frames, and Docker because building OpenCV with FFmpeg is surprisingly difficult. So we just wanted to do it once and then build a Docker container for it so that if people wanted to use our code, we could just have them run a few commands. And if you go to our website, there's a blog post about getting the Docker container and running it. And a little bit more background about OpenCV, because that's mainly what we're going to be talking about today. Basically, OpenCV is just a collection of highly optimized computer vision algorithms. It's written in C and C++, but there are bindings to Python and Java as well. And it can be run on a bunch of different platforms. And it's just like a very popular library that's well maintained. So a little bit more about the subject of our experiment. We're having people look at artwork. We decided to do artwork because natural viewing is really important in that scenario. So like viewing artwork on a screen, as you can imagine, is very different from viewing it in a museum in like a very natural setting. So we wanted to capture that. The 2 pieces that we used were called Decompositioning by Jeff Sonhaus and Family Tree by Wangechi Mutu. Family Tree is actually a collection of, I think, 12 of these types of images. They're like abstract face representations. So we actually chose both of these pieces of art for their abstract representations of faces. Now you may be wondering, why did we choose faces? So this is where the neuroscience comes into play. We know certain things about viewing faces within neuroscience. We know that if there's a face in an image, people tend to gravitate towards that and look at it, as you can see in that image towards the bottom. That's just like a heat map, which is a common analysis done with eye tracking. And basically, the redder or the warmer the color, the more that people were looking at that part of the image. So they're very focused on the face here. And then we also know that within faces, people tend to look at the eyes and the mouth, and that's demonstrated on the image to the right. So the purpose of our experiment is that we wanted to see how much these things translated to more abstract representations of faces in artwork. So how did we do the gaze mapping to the static image? This is a frame-by-frame process. So for each frame, we attempt to find the static image within that video frame. And then if we find the static image, we try to find the relationship between those 2 spaces to account for perspective differences. And finally, once we have that relationship, we apply that to the eye tracking data. So we have eye tracking data with respect to video coordinates, and we get out eye tracking data with respect to static image coordinates. So step 1 is finding a match image in our video frame. So this seems like a very hard problem, right? Like you're trying to find an image within another image, but it can be from any perspective. But luckily, it's very well studied within the computer vision community, and there are some pretty good solutions for it. So this can be broken down into two substeps. Basically, first we want to find descriptive features of each image that can be compared between the two. And then we want to match features that are similar between the two images. So OpenCV provides a lot of different feature detectors. Some of these are edge detection and corner detection, but these aren't really what we want because they're not really robust or descriptive. So we can't match corners that are found because it's just finding corners. So we want features that are descriptive. So the answer to that problem would be using SIFT features, which stands for Scale Invariant Feature Transform. And these are robust to, obviously, it's scale invariant, so they're robust to scale as well as perspective, and they provide a rich description of what is contained inside the feature that is found. So each SIFT feature gives you a point and like a size that it corresponds to, as well as a 128 dimensional feature vector that basically describes what is in that feature that it's found. And you can use that to compare across features and find similar features. So these are the SIFT features calculated for each image. On the left, a video frame, and on the right, our matching image. And as you can see, some of the features correspond to a larger size, and some of them correspond to a smaller size. But the feature descriptors will remain the same no matter the size of them. So like, for example, on the video on the left, if someone were to walk back 10 steps, those features would still have the same feature descriptors, but the sizes of the features would change. So once we have features for both images, we can match them. And we do this with an algorithm called FLAN, which stands for Fast Linear Approximate Nearest Neighbors. So regular nearest neighbors, the basic process for that would be for each feature in the match image, you would want to find the closest feature in the video frame through Euclidean distance. And Euclidean distance is basically just like if you have like 2 points, let's say you have 2 points in a two-dimensional surface and you draw a line between them, the distance of that line, Euclidean distance is just generalized to n dimensions. So in this case, it would be 128 dimensions of the feature space. So we're finding the closest straight line between two features. So that's regular nearest neighbors, and we decided to use the approximate nearest neighbors algorithm because it's a lot faster, and we found that we don't need to find exact matches most of the time, and that the approximate nearest neighbors, as you can see here, does a pretty good job of matching the similar features. So once we have those matches, we need to find the relationship between the frames, so the video frame and the static image. So how do we define this relationship? We can define it as an affine transformation, which is just a transformation that preserves points, straight lines, and planes, but it can account for changes in perspective. So no curvature can be added, but it can account for changes in perspective. So if you look at this image to the right, each leaf in that image can be obtained by an affine transformation on another leaf. So reflection, rotation, scaling, shear mapping, those can all be accounted for by an affine transformation. So how do we parameterize an affine transformation? That would be with something called an affine matrix, which is just a 3x3 matrix that you can apply to an image and get the affine transformation that corresponds. So the affine matrix is what we need to find, the affine matrix that corresponds to going from the video frame to the static image. So how do we find that affine matrix? There's a function in OpenCV called find homography. And basically what this function does is it takes a set of source points and a set of destination points that correspond to each other and finds an affine matrix that fits those data. So in this case, we would be taking our matching features, our set of corresponding matching features, and finding the affine transformation between them. And we have to specify a method for this function for find homography, and we used something called ransack. And the reason we use that is because it's robust to outliers. So let's say, if I go back here really quickly, let's say you have like, so most of these look like they're fitting pretty well, but let's say you have one that just like matches this corner over here. So that would be an outlier because it's not the same affine transformation as the rest of the points. What ransack does is that it's robust to outliers. So you can have, we can use our approximate nearest neighbors algorithm because like it's going to be accurate most of the time. And when it's not accurate, when we're finding the homography matrix, the affine matrix, this ransack method will ignore those outliers. So this image on the right demonstrates the affine matrix being applied to the video frame. So basically, you just send in the video frame, use find homography, and then another function called apply perspective transform or something like that. And then you get the video frame in the static image space. And as you can see, it's cut off at the top because in the video, the top of that piece of art was cut off, but the coordinates all line up, which is pretty cool. And this can actually be applied in the other direction simply by inverting the matrix. So you can go from the static image coordinates to the video frame coordinates just by inverting the matrix and then applying the transformation on the static image. So once we have this affine matrix, we use the perspective transform function that I mentioned earlier on the gaze data for each video frame because we already have a transformation from video frame space to static image space. So that's essentially what we did. And now Jeff is going to come up and talk about some of the extensions that he's been working on.
Excellent. Yeah. So now we have the ability to map these gaze locations from the video reference frame to a static reference image, and this allows us to start doing some more traditional eye tracking analyses. So now that we can provide this mapping, we can start with basic questions like, well, what parts of an image is the person looking at most over time? One way to do that is simply just to map all of these gaze locations onto that static reference image and see these are all the areas that the person looked at. An alternative approach is to start making heat maps on these static reference images. In this case, we're calculating a two-dimensional kernel density estimate over all the available gaze points that are here, and we produce this summary map. And this map is going to be indicating which parts of the region the person spent the most time looking at. In this case, on this example taken from the video, we can find that people spend the most time looking at the head and face regions, which is what consistent with what would be predicted from traditional eye tracking analyses on static images. And to produce a map like this, we took advantage of the Seaborn plotting libraries in Python. And in the spirit of this conference, I want to give a nod to that library. They produce some really easy to implement and really aesthetically gorgeous plots. So check that out if you haven't already. So you can collapse across the entire session as we've done here and use a library like Seaborn or Matplotlib to produce a visualization that summarizes the entire viewing behavior over the entire session. Or you can start creating heat maps that are evolving over time. So get this to play. Where's the mouse? There it is. So in this case, we have we're calculating those kernel density estimates on every new time point as it's acquired, as every new frame as it's acquired. And then we can write the new plot as a frame in its own video, and then use that to show the evolution of the gaze and viewing behavior over time. So before, when I showed you that static image that was summarized over the entire session, all the attention was spent on most of the fixations were on the head and face region. But if you could see in the beginning of that video, the person starts out at least focusing on the lower left quadrant of the image, and then over time kind of shifts their attention more up to the face. And as Shariq mentioned earlier, we have a transformation matrix, right, that will go from the video frame to the static reference image. But you can simply invert that matrix, then you have a new matrix that will map from the reference image back into the video frame. So all these plots that we're doing, we can then take and then overlay directly on the original source video itself. Oops. Was that playing? Did you see that? Yeah, so anyway, so in this we were mapping the gaze location from the static reference image, producing that kernel density map on the reference image, and then projecting it back into the video itself. Did you see it for a second at all? At least was it playing? That's fine. It's let me see if I can go back a slide. Yeah, so in this we're taking it and then just projecting it back into the original source video itself, so you can overlay these visualizations directly onto the source video. Yeah, sorry about this. Where's the mapping thing? Present mode.
Like present, and then we'll click on the. So if you click on, sorry, one second.
Get back to the. Okay, perfect. Okay, sorry about that. All right, so great. So we've been talking about mapping from the reference, from the video that we're collecting onto a static reference image. And this is really useful for some of the basic eye tracking analyses we want to do. And this opens up a lot of new possibilities for allowing participants, if you're running an experiment, unconstrained, free movement as they're walking around in an environment. This freedom with it, though, adds in a lot of new responsibilities that are kind of a headache from an experimental standpoint. If your person's moving around, you'd like to be able to track where that person is in space. And everything we've been talking about so far is mapping between two-dimensional planes. So we have the two-dimensional video and then the two-dimensional static reference image. And we started to ask about, okay, well, would there be a way to figure out where the person was in the room using the information that we already have access to, either sensors or things like that? So our first approach was, Shariq mentioned earlier that there's accelerometers and gyroscopes that are built into these glasses, and so we're like, all right, well, as long as we can know the starting location or assume a starting location for the person, these sensors should be able to tell us something about how they're moving over time. If anybody's ever done this in their own work, it's a great idea in theory. In practice, these sensors, like all sensors, have a bit of measurement error to them. And when you're trying to get to position from acceleration, you're integrating twice. You're integrating first over acceleration to get to velocity, and integrating over velocity to get to position. And as such, the influence of these tiny measurement errors can compound exponentially over time. So if you're looking at acceleration alone, you can't really see the figures on the y-axis there in that middle plot, but after about a minute and a half, the person's moving at 40 meters a second. Which, yeah, for reference is also the same speed that the DeLorean has to go back in time. Yeah, and so then by the time you get to position, after a minute and a half, the person's not only not in the art museum anymore, but they're about 1.5 kilometers away from the museum. So there are probably ways that we could optimize this and improve that somewhat, but we're talking about errors that are 2 or 3 or 4 orders of magnitude different from what we would think would be ideal. So we went back to the drawing table and started asking, like, okay, well, what if we'd be able to infer position from the camera itself, from the frames that are being recorded from the camera? The challenge with this approach is that a camera sensor, much like the retina in our eyes, collapses the 3-dimensional world onto a 2-dimensional representation, a 2-dimensional plane. So this means that there are an infinite number of 3-dimensional objects in the world that will produce the exact same 2-dimensional projection. A bigger object farther away will look the same as a smaller object that's closer to you. The corollary to that, though, is that if you know what the object in the real world is, any single unique object will produce one and only one 2D projection onto a camera frame. And it'll tell you where, depending on where that object is, that projection on the camera frame will be unique. In our case, we're working with works of art in a museum, so of course we'd know the actual size of these pieces in the real world. In computer vision terms, this is what's called the perspective endpoint problem. And it turns out to solve it, you need to know not only the size of the object in the real world, but you also need to know to what degree is your camera lens distorting the images that are coming in. And thankfully, OpenCV has tools that will help you with both of these steps. So the first step, like I mentioned, is figuring out how is your camera distorting these images. And to start working this calibration, we can collect a set of images of a known object. In this case, we're using a chessboard. Collect a lot of different images from different vantage points. Get closer, change your perspective, things like that. And using a chessboard pattern is really easy, and in fact, OpenCV includes a chessboard PNG file that you can download, print out, and paste up on your own wall, as well as functions that it will have that are specially designed for finding the corners on the grid of the chessboard. And since you know what the relationships between the corners and the chessboard should be, measuring those relationships on your image will tell you something about how the images are being distorted. So once you get enough examples of this, 10 images or so, you can get an overall sense of how your camera is distorting your images, and you can go on. The nice thing about that is that it only needs to be done once per camera. As long as you don't change your lens, those distortion matrices will always be the same. So you can save it as a JSON file or something and use it on every analysis that you have going forward. Okay, so now that we figured out the camera calibration, next goal is to figure, well, where was the camera on every frame of the video that we have? And we begin by using the same steps that Shariq mentioned earlier, where we used the SIFT feature matching to find corresponding locations between the video frame and the reference image. Every feature that we've identified on that step will be expressed in terms of pixel locations. It'll be either pixel locations on the video frame or pixel locations on the reference image. We need to take all of the features that were identified on the reference image and convert those into real-world coordinates. So we define a coordinate system for our world. For simplicity's sake, it works really well to define the z-plane. You can see that as the wall that the artwork is mounted on. That means that any feature that is converted will have a z dimension of 0, which makes things relatively easy. And then the x and y locations you can get by calculating a pixels to centimeters or units or whatever your real world unit is conversion factor, and then multiplying all of your pixels by that conversion factor. So for example, if we identified a feature here that was at pixel location 340 by 250, that would correspond to a real world location of about 48 centimeters, 35 centimeters, and 0 centimeters in the z dimension in the real world. And we apply that same conversion to all of the features that we have. So once we have all the features defined in 3D world coordinates, you can use OpenCV function solve PNP ransack to figure out where the camera was on that frame. And this will return the rotation and translation matrices that will go from the camera to the real world object. And in this case, the artwork is fixed in space, and so we're trying to, and the camera's moving around it. The camera that somebody's wearing is moving around it. So we invert those matrices to really get a sense of where the camera is with respect to this fixed location in space. And we do that on every frame of the video. And of course, the accuracy of how well you do this depends a lot on how well that stiff feature matching works. Inevitably, there's going to be some frames where the person was moving really quickly, say, and it was really blurry and there wasn't a good matching happening there. But if you look at it, it's pretty easy to actually identify where those problematic frames were. So on the left, we have this is a plot of the raw z dimension of where the participant was, and you can see the spikes in there that are the places where the people are. The stiff matching isn't working very well. And then on the left, you can just apply some basic spike filtering, smoothing to get a smooth estimate of this person's motion along this dimension. And we can do this a lot for all the motion and orientation parameters. So at this point, we know on every time point, every frame of the video, a lot of information about the person, what they were doing. We know where they were looking, we know where they were in space, and we know how they were oriented. So from this information, we can start to reconstruct the movement and viewing behavior throughout the experiment. It's like, here's a movie where we do just that. Watch me try to not break it. So in this example, we're showing you a 3D reconstruction of the participants' behavior throughout the course of this. We see where they moved, how they were positioned at every time point, and importantly, where they were looking at in time. And we can also start supplementing this with additional measures that weren't present there. So the circle that's showing you their gaze location on the artwork is sized according to the approximate extent of visual focus based on their distance and visual angle, the fovea and the retina. So this is a movie that we created, but the actual the model was created using JavaScript. It's a 3JS library for 3D modeling, which is really nice. And so the web version of this is interactive. You can pan, zoom around, and scrub back and forth in time, and really get a detailed look into what this person's doing throughout the course of it. Okay, so just to wrap up some of the things that we were talking about here, I think the dynamic object and gaze tracking that we've been presenting is, I think, going to open up a lot of new opportunities for eye tracking research going forward. Unlike most studies, this allows your participants to have free range of motion throughout the room and behave in a more naturalistic setting, unlike sitting in front of a computer screen with, in a laboratory, say. And despite this freedom, the methods that we've been discussing allow you to really robustly quantify and characterize viewing behavior on static reference images, similar to what you'd want with traditional eye tracking, as well as record movement. And we've outlined a way that you can cleanly and reliably translate between these three different coordinate systems we have: the video, the reference image, and the 3D environment that the person's in themselves. And best of all, this mapping is done automatically. There's no need to painstakingly go in and manually identify features on your reference image or on the video or anything like that. It's all can happen programmatically. So great. So just wanted to say thanks to John in the Pearson Lab, Elizabeth Johnson at the Duke Institute for Brain Sciences, and Maureen Wardle at the Nasher Museum, who've all been really helpful on this project for us. And thank you for listening.